This is my colleague and friend Andy Strominger. We've known each other since graduate school, and he's now a leading string theorist and a colleague in the physics department here. Andy's been kind enough to join in our MOOC to talk a little bit about black holes and why they represent the laboratory for thinking about general relativity even these 100 years after the invention of the Einstein equations. So welcome, Andy.
Thank you.
The first item of business is to try to figure out or to explain in a kind of compact form what a black hole is and why relativity, general relativity, became important for it.
A black hole is a region of space in which the force of gravity has become so incredibly strong that nothing can escape, not even light. So nothing ever comes out of a black hole, and that's why they're black. The beginning of the very long and still unfinished story of black holes was Schwarzschild's work in 1915, shortly after Einstein wrote down his field equations, in which he showed that Einstein's theory of general relativity predicts the existence of black holes. Now, it took another half century to understand this prediction. And Einstein himself denied that black holes existed in his theory because they're such bizarre, radical objects, and they're so hard to understand that the simplest solution to this was that they just don't exist, they're not there. Schwarzschild has misunderstood the equations.
Is there a way to understand what it is that Einstein didn't like about black holes?
What he didn't like about black holes is that in the very center of a black hole, once you've fallen through the outer boundary of it into the middle, there's a place where the forces of gravity become infinitely strong. They would crush anything. The strongest steel would just be obliterated and sucked into a point in the middle of the black hole. And this means, this infinity means that Einstein's theory of general relativity itself must break down at the middle of a black hole. It's good until you get to the very middle, but when you get to the middle, it breaks down. So I guess he didn't like the idea that his theory predicted its own demise, that it showed that it was general relativity was good most of the time, but inevitably it would ultimately break down. And he was unhappy about this, and many people were unhappy with this, but now I think the modern view is that this is a wonderful thing, because we know that all theories of physics sooner or later break down, but few of them are so kind as to point to the place exactly where they're going to break down. And this is what we have in the case of Einstein's theory of general relativity. So we know exactly where to look to try to understand what is beyond general relativity. So black holes are the most interesting objects in general relativity, and they've also advertised themselves as the portal to the next level of understanding of the laws of physics.
Where does it leave you with your feeling about Einstein's equations of general relativity? Does general relativity seem to you different in some way than it did before you began your work on problems of black holes?
You know, it's just kind of incredible that somebody would write down a set of equations, and 100 years later, we're still finding new meaning in those equations and things, basic things that we didn't know about them 100 years later. My sense of the depth of those equations and what they have in them, we keep mining them and learning more from them, but there still seems to be more to offer. The field is very far from having been closed down. I mean, even in the last 5 years, conjectures about the nature of those equations that have been standing for 40 years have been disproved. In this discussion that we've been having, there are three basic areas that enter into play. There's Einstein's theory of general relativity, and there's quantum mechanics, and then we've also been talking about information. There's information theory and statistical mechanics. And the puzzle that we've been discussing involves all three of those at once. And these, in a sense, are the three basic areas of modern physics. And there's some connection between them, some very fundamental connection between them that we understand little pieces of and get little glimpses of, but don't understand in entirety. The other feeling that I've had as I've been working on these problems over the decades is that there's something very fundamental that we don't understand about physics and the universe around us that nevertheless might be within our grasp, sometime in the next coming decades.